So let's talk about uncertainties. What do they come from and how to evaluate them numerically? Well, let's first of all recall our data. So this is XY, it's our training set, it's what we use to fit the model. And this is the regression coefficients we got by making this fit. And these are the predicted values we got by using these regression coefficients, right? Now imagine that we have a new person in this data. So this is not a part of our training set. And this person has 165 centimeters height. So we would like to use our model to predict the weight of this person. Well, we can do it easily, right? So we simply take 165, multiply to B1, it's a slope, right? So we know that for every kilogram, for every centimeter, we should take 1.3 kilograms, right? So this is the effect of height on weight. And then we subtract 151. So this is the result. So this is the predicted weight of this person. So this is the predicted weight of this person. But the question is, what's the true weight? We know that the true weight, of course, the predicted value is not always the same as the real value, right? It varies. Sometimes a big variation, sometimes small variation, and so on and so forth. But can we predict the real Y value based on this predicted value? For example, in form of interval, like a confidence interval. So let's talk about this. So the overall idea is that your real Y value, it's your predicted Y value plus error margin. And this error margin is caused by variation of this residual. Sometimes it's 0, sometimes 1, sometimes 2. It can be even bigger, 3, 4, 5, and so on and so forth, right? And the idea is that if we can estimate the error margin, if we find out where this error comes from, we already know a little bit about that, and then use statistics to estimate error margin, we will be able to predict, not to predict, but to estimate the real Y value, in this case, weight of this person, the real weight of this person, with a given confidence and as a confidence interval. So we know with a given confidence that the true value will be inside. So that's exactly what we are going to talk about in this video. Well, first of all, this is my value that I estimated, 63.5, but we're missing error margin. Well, strictly speaking, the error of the prediction has two sources. The first source is called fitting error. It tells you how well your line fits the points, and that's what we already estimated, because that's the fitting error you estimate for your sample. So how well your line fits the sample points. And you remember that we can estimate it by using standard error. Of course, we can also use R-squared and so on and so forth, but for error margin, we need something that has the same units as Y value, so that's why it's standard error. And therefore, because residuals are normally distributed, we should use approximation of normal distribution, t-distribution, because sample size is small, you remember, right? We don't know the real sigma in this case, the real standard error. So in this case, we can take plus minus t standard errors in order to get this error margin. But this error margin will only be caused by fitting error. Okay. The second source, it's the sampling error. And that's exactly what the sample-to-sample variation, right? So this is how far your sample is from the population, because strictly speaking, we would like to estimate parameters of our model, slope and intercept, for the population. But we got statistics, the coefficients of our model for our sample. And likewise, the B0 varies around the beta. So beta is here, and then B0 varies around beta 0. And B1 also varies around beta 1, right? So we need to find out how to estimate the standard error of these two coefficients, how big this variation can be, and then somehow estimate the effect of this variation to the error margin. Okay, that's what we call a sampling error. Sampling error comes from uncertainty of regression coefficients. So let me show you how to do it step by step. Let's start with fitting error. You remember, this is, for example, this is another example. It's not these 5 points, but it's just to show the fitting error a little bit better. So you can see that the points vary around the line, right? So you don't have points exactly on a straight line. And this variation, how far the real Y value can go from the predicted Y value, that's exactly the fitting error. And we already know how to estimate it. It can be even better if I show you the population, right? So you can see that for population, you can clearly see that you have fitting error. Moreover, this fitting error doesn't depend on x, right? So for all x values, the fitting error is more or less the same. and we already know how to estimate it. This is the standard deviation of this variation, right? Of course, this standard deviation is estimated based on our sample. This is why we need to use t-distribution in order to get the interval caused by this fitting error. Okay. So that leads us to a very simple solution, right? So we take a standard error. We know how many degrees of freedom we have. So we can compute error margin caused by fitting error by simply multiplying a t-score for given confidence to the standard error. How to get the confidence? How to get the t-score? Well, we know we, for example, want to have 95% confidence. If it's 95% confidence, you remember that these are all possible t-scores, right? Here we have 0. And then we need to find t1 and t2. And you remember t1 will be just a negative of t2 for this area. So inside you have 0.95. Well, you remember that this area will be 0.025. This area will be 0.975. So to get the positive one, I use 975, 3 degrees of freedom, and that's the t-score. So it means that I should take 3 standard errors for calculate confidence interval for the 95% confidence. Okay, so I can do that. So this is my standard error. This is my t-score. So this is the error margin. So this is how big the uncertainty is caused by only fitting error. Caused by only fitting error if you don't take into account sampling error. And this is the value, right? So this variation we estimate with 95% confidence. So it means only for 95% of the points, of the data points, right? It's plus minus 6, plus minus 5.8 kilograms. Okay. Now let's talk about sampling error. So how much sampling error adds on top of the fitting error? Well, in order to understand sampling error, let me show you the Grasta app again, but this time I will just introduce it in the same video. If you want, you can try it later. Either go to Grasta if you watch this video on YouTube and play with this app, or you can, if you watch this video in one of my e-learning platforms, you will get this app just in the next step. Okay, so let me switch to the app. So this is the Grasta, and the app you need is, if you scroll down, you will find out this covariance and regression block, and then what you need, it's a sampling error and overfitting. So click try here. This is it. So what you see here, well, the gray points, the gray line, and the gray bars are population. So for example, you can see that I have a lot of gray points on the big plot, and I have 2 gray bars on the small plot, right? So the gray points is population, it's just x and y values, and the gray bars shows you the regression coefficients. You can see the true regression model for the population here, also in this corner, and this is the 39.59 SB0 and 65.73 for B1. Now the blue points, the dark blue points, is my sample, is my current sample, and then you can see that the sample size is equal to 10. And then you can see that the B0 and B1, its regression coefficients are not the same as the population regression coefficients. Moreover, you can see that the blue line, it's the line which I fit with my sample, is not the same as the dark gray line, right? So it means that I have uncertainty. My sample or coefficients of my sample are not the same as the coefficients of my population. And you can also see it on the small plot. If you look at the blue circles, you can see they are far from the bars. Not far, but for example, B1 is pretty close, B0 a little bit far. Now what I'm going to do, I take a new sample. You can see that now the position is a little bit different. The line is different, the coefficients are different, and so on and so forth. If I keep taking a new sample many times, you will find out that these lines from the previous sample, they form a certain pattern. You can see it here, right? So and you can also see how big the variation of B0 and B1 is. They always vary around the true population coefficient, but they vary. That's the most important. And the idea is following. So let me now get back to the slides. So this is just a screenshot of the previous of the Grasta app. You can see that the more far you go from the average x, so this is the average x, in this case is 0. The more far you go, the bigger will be effect from this uncertainty, from the sampling error. But in the middle, the effect is small. So what it means? It means that the effect depends on this distance. So for a given point, if you want to estimate effect from sampling error, you need to take into account this distance. So that's one thing. The second thing, let me again show you this app, but this time I will change the sample size to 30. And then if I take a lot of points now with 30, you can see that this effect is much smaller, right? So this variation of the line is much smaller. If I make a sample size of 100, the variation will be tiny compared to the sample size of 10. And if I have a sample size of 5, you can see the variation will be much larger, right? So you can see it's sometimes it's really big variation, like for example this line. Now the second takeaway is that the variation depends on the sample size. So it means that we need to take into account how far value is from the average. So x value is from the average x, right? And then also we have to take into account the sample size, but we can see that it's kind of the inverse, right? So the bigger sample size, the smaller error is. So now let's take this all into account and make adjustment of error margin for the sampling error. So this is it. This is how it looks like. So this is sampling error without fitting error. You can see it has two terms. The first term is this one. It shows you the dependence on the sample size. And the second term, look, this is how far x goes from mx, but we are interested only in the distance. We don't care if it's negative or positive, so therefore we square it. But how big this distance is depends on how big the variation of all x variables are, right? All x values are. And this is why we use a sum of squares. So it means that it's sum of all these distances for all the other points that we use to make a model, right? So this is variation of the training set. So this is like a unitless measurement how far your value goes from the average value. Okay, so these are two contributors to this sampling error, and then this is how to compute them, right? So you can see that we have sum of squared x values, sum of squared y values. We have sample size. We know the sample size, so we can simply put it here. So you can see we have this TSE that we calculated before. So this one plus 1 over 5 because the sample size is 5. This is our x value, this one. This is our x value. This is average x. This is average x. We know it from here, right? And this is the sum of squared values for all x variables from the training set. And then by computing all this, by finishing these calculations, we can get the error margin caused by only sampling error. This is only sampling error without fitting error. Okay, so you can see it's like approximately 2.7 kilograms. Because sample size is small, it's relatively large. When your sample size is approximately 30 or larger, then sampling error will be negligibly small. You can even sometimes ignore it. But when your sample size is relatively small, then this error is relatively large. Okay. Now let's learn how to combine this together. So how to combine the fitting error and the sampling error? That's simple, right? So this is the fitting error. This is the sampling error. You can see you have TSE here, you have TSE here. Well, if you want to combine two errors together, you need to sum up the variances of these errors, right? So it means that you need to square it and take a sum of squared values. So this is the total error margin squared variance. This is error margin squared for the fitting error. This is error margin for the sampling error, right? So that's how to do it. So this is square it. This is square it. This is square root of square root is gone because we square it, right? And then you can see that this and this are the same, so we can take it out from outside the parentheses. That gives me this one. Okay. So this is how to combine these two errors. And now if you remember, this is the square root. So if you want to get the real error margin, in this case, you need to take a square root, and this is the final equation, right? So you can see this little one here, the red one, it's the fitting error, and this is the sampling error. This is the sampling error. So this is how to compute the error margin. Now let's do that. So we know all the calculations already. So this is 5.82, 1, 0.2, it's 1 over 5. This is the distance, x from m, right? And that gives you the adjustment. So you can see that without sampling error, it's 5.8. When we adjust for the sampling error, it's 6.5. So this is the final total error of prediction. And this is how to show it. You remember it's 95% confidence. And it means that with 95% confidence, the weight of this person that has height of 165 centimeters is between 56.5 and 70 kilos. So that's our best estimate in this case. Okay. So this is how to do it. So every time you make a prediction, you can also relate this prediction to reality by computing confidence interval for your predicted value. And this confidence interval contains these two uncertainties, the fitting error and the sampling error. Okay. So this is just to sum up. So you have uncertainty from the regression coefficients, it's a sampling error. You have uncertainty in the predicted values, it's a fitting error. And the sum of these two uncertainties is what you use to estimate the confidence interval of the real y value. Okay. Now let me show you another app that shows you these both two errors in a nicer way. And in the next video, you will see the introduction to this app. And then after that, I recommend you to go to Grasta, or if you watch this video in my e-learning platform, you just take the next step in this sequence and then play with this app a little bit after watching the next video.